More and more children are out of school, but parents don't want math learning to stop. They're turning to Mathnasium at home. Real-time math instruction tailored to your child's exact educational needs. It's the same face-to-face live instruction used in our centers for over 15 years, now on a computer. Your child can keep their math skills sharp, catch up, or soar ahead, from home or anywhere with an internet connection. To learn if Mathnasium at home is right for your child, visit mathnasium.com/at-home. Mathnasium at home, changing lives through math.
Hello everyone, welcome back to the Mathnasium Schoolhouse. I am John, the AVP of Education and Training for Mathnasium. And I am really excited for this topic today. It's one of my favorite topics in mathematics. It is a conversation around what we call the Fibonacci sequence and kind of touching on an introduction to a mathematical constant. We'll call it phi. Some people call it phi. I'm going to call it phi. But in any event, not unlike pi or e, there's kind of a beautiful mathematical constant out there that has a connection back to the Fibonacci sequence. In terms of what you need today to follow the lesson, we're going to add, we're going to multiply, divide a little bit. And this is probably one of the rare occasions that I would say if you have access to a calculator nearby, you may want to have it. In Mathnasium, we spent a lot of time developing number sense and mental math. And I don't know, hopefully you were with me on Wednesday talking about mental math strategies, and we'll continue that next week. But when we're exploring this, there's going to be a lot of addition. There's going to be some division that, maybe you haven't done too much division, or it might take you a little while, and that's okay. The division will end up having decimals, and there's going to be a lot of it. So it might be better if you had a calculator nearby. I want to focus more on some of the really cool and interesting properties of the sequence, more so than the computation. What I would encourage certainly is if you're practicing later, or if you're a parent, maybe watch the video again later and slow it down and pause it and work on some of the computation and the mental math. Because it's beneficial, like I said. But we only have so much time together, and I want to make sure I show you as much as I possibly can. We could talk about this subject 20 times, and there would still be more to explore. So with all of that said, I want to dive right in. And my first question, and as hopefully you're introducing yourselves and where you're from, and if you're a parent, certainly introduce yourselves as well. If you're at a Mathnasium watch party, or if you're a Mathnasium student, tell everyone what Mathnasium you're from. What I want to start with is we're going to be talking about something called the Fibonacci sequence. So I wanted to start with a question as to what a sequence even is. So if you want to type that in the comments, that would be great. But before we start looking at them, I thought it would be helpful to just talk about what a sequence is. So I gave you some examples of sequences, and I gave you what their names are. So the top, and some of them may look very familiar to you, and you may even be thinking of how they were created. And we're thinking of a sequence in this instance as being a group of numbers that have a certain property, and where order matters. And when we're thinking about an arithmetic sequence, like at the top, you can see I started it at 5. I added 6 each time to create that sequence of numbers. The 3 dots that you see here just represent the fact that it will go on forever. If I wanted to continue adding 6 over and over and over again, I could do that. And if you're looking for something cool to practice at home, pick a number to start at, pick a number to add to it, and see how far you can go. See how far you can go mentally. It's a good thing to practice. And it stretches your brain, which is really important. There's also something called a geometric sequence, and maybe you want to type in the comments what that rule is. The numbers get big pretty quickly in this one. But geometric sequences have what are called a common ratio. They're multiplication sequences. So that one starts at 2. I multiply by 3 each time to get the next number. And it goes on forever as long as I want to continue to multiply. Harmonic is interesting, and I want to, do you see a connection between arithmetic and harmonic? And if you said that they're reciprocals, you're right. If I have an arithmetic sequence and I take the reciprocal of each term, I create what's called a harmonic sequence. So if you want to practice at home, you can create an arithmetic sequence and flip them, which is kind of cool to think about. In any case, those are some sequences that, exist, and maybe you've seen some of them before. You're thinking about patterns and start count bys and starting at a number and counting up by a number, or multiplication for that matter. But I want to focus today on what's called the Fibonacci sequence. That's why we're here together today. And Fibonacci was an Italian mathematician that lived in the late 1100s to about the mid 1200s. And he certainly brought to the forefront these Fibonacci numbers, but he didn't invent them or wasn't the first to put together their unique properties. They had been known for centuries, but he certainly popularized them. And he's also, probably his greatest contribution is popularizing the Hindu Arabic numeral system, which is the most popular numeral system in the world. It's the most commonly used. So very important person in the history of mathematics. So I'm going to write the Fibonacci sequence down for you. Okay. And maybe some of you have seen this before, and you can comment if you have, and you can comment if you know what the rule is. And that's not all the entire sequence. It goes on forever as far as I ran out of room, but as far as I want to calculate it. So my question is, first, what is the rule? And you can type in the comments if you know what the rule is. So this sequence is cool because it's every term in this sequence is the sum of the two before it. So 0 plus 1 is 1, 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, and 8 plus 13 is 21. Okay? So it's a little bit of a different type of sequence. And sometimes when you're creating sequences of numbers, you do more than one thing. In this case, we're actually combining the two things that are before each number and putting it together. Okay. Sometimes when I write the sequence down today, or if I write down the numbers themselves, I may not include 0. Back in Fibonacci's time, he actually didn't. The history of 0, if you want to study something cool, there's actually a really extensive history on the number 0 period, which is really interesting. So sometimes I'll write it and sometimes I won't. Sometimes when I'm talking about the Fibonacci numbers, I may only pick certain ones. But the important thing to know is how the sequence is created, and that it goes on forever, and I can pick any numbers from the sequence that I want, and they're called Fibonacci numbers. Now my question to you next, before we move on to some of the cool properties around the Fibonacci sequence, is what are the next 4 numbers in the sequence? If you were going to continue the pattern, what would those be? So remember, if I want to know what comes next, I have to add these together. Okay. So 34 would be next. 55, 89, and 144. Those are the next four. And again, if you want to practice something, keep adding and see how far you can go. Actually, here's a list that I found of the first 36, and you can see that they get big fast. By the time you get to the 36th, you're already at almost 15 million, which is pretty big. But this is a great way to practice your addition and see how close you get to those numbers. So let's move back a little bit. So I gave you some of the Fibonacci numbers there. And my question to you is, I want to start looking at some of the properties around these numbers and some of the cool tricks that you can show other people. And what I want to do is I want to start pairing them and multiplying them and finding the sum. And what I mean by that is I'm going to multiply 1 times 1 to start. And then I'm going to add 1 times 2. And then I'm going to add 2 times 3. And what I really want you to do is focus on this number here, which is the last number. It's where I stopped. And I'll tell you why in a moment why I did. But what do you get when you calculate that? So this isn't too bad. 1 times 1 is 1, 1 times 2 is 2, and 2 times 3 is 6, and 1 plus 2 plus 6 is 9. Now remember, I asked you to focus on the 3. What's 3 times 3? And if you've been practicing your multiplication, you know that's 9. Okay, let's look at another one. I'm going to show you why this is how this works. So I'm going to start at the beginning. I'm going to add 1 times 1 plus 1 times 2 plus 2 times 3 plus 3 times 5 plus 5 times 8. And again, I want you to focus on this last number, 8. And I want you to look and see what happened here. And what do you think you'll get if you were to add all of those together? Maybe type in the comments, take a guess, an educated guess. And if you said 64, you're right. 1 times 1, let me change my color here. 1 times 1 is 1, 1 times 2 is 2, 2 times 3 is 6, 3 times 5 is 15, and 5 times 8 is 40. And if you add all of those together, you get 64. Now the way this works is, if I have an odd number of products, so in the first one we did together, I had 3 products. In the second one, I had 5. If I have an odd number of products that I'm adding together, then the sum, when I add them all together, is equal to the last number times itself, always. Which is really cool and unexpected. But that's why math is so awesome, because there are so many cool things going on. So here's one for you to try later. And I'll put this in your practice worksheet. So remember, if I have an odd number, so I have 1, 2, 3, 4, 5, 6, 7. If I calculate all of those and add them together, then it will be the last number times itself. Always. And you can test it later, because I know that's a lot to calculate. So you can prove that later, okay? So here's another, so these are all Fibonacci numbers, okay? I just picked from the middle of the list this time. And what I'd like you to do is add them all together. So I'd just like you to take them and add them. So like I said, if you had a calculator, it'd be helpful because that's a lot to add kind of on the spot. Or just watch the video later and try to do it by hand or use mental math, practice that too. But it's really important to know that there are 10 numbers here. I chose 10 for a reason. And what do you get if you add those together? I'll give you just another second. If you got 1,584, great job. But the cool thing is that if I pick any 10 numbers in the Fibonacci sequence, any 10 Fibonacci numbers, and add them together, it is always divisible by 11, always, which is kind of a cool thing. 1,584 divided by 11 is 144. It's always divisible by 11, and that's one way to check and see if you're right. So you can pick any 10, add them up, and it will always be divisible by 11. So here's one for you to try, and I'll give you a minute to try it. So there's a different 10 Fibonacci different set of Fibonacci numbers. There are 10 of them. We'll give you a moment to add them up. But you'll know you're right if the sum is divisible by 11. Or it's one way to check, anyway. If you got 143, you're right. And 143 is divisible by 11 because you get 13. So another cool property of the Fibonacci numbers is that the sum of any 10 of them is divisible by 11. So something to try out and practice too. That's a 9, sorry. So here are some others. Okay. And what I'd like you to do here is add these together. And then I want you to focus on this number here. So what do you get when you add them all together? That's the first question. So what is the sum? And again, I've chosen 10 numbers for a reason. $374 is the sum. And this property is cool because if I have any 10 Fibonacci numbers, the sum is always equal to the 7th number times 11. So if I'm trying to find the sum of any 10 numbers, then all I really need is the 7th one. And if I multiply that one times 11, I will always get the sum. And I don't have to add all of those together, which is really cool. And again, something to practice. So take a list of Fibonacci numbers, pick any 10, find the 7th one, multiply times 11, and see if you get the exact same thing as when you were to add them all together. And you always will, which is a lot of fun. Here's another set of numbers. I went a little bit further this time, so I went all the way out to 233. And again, I would ask you to add them. So see what you get if you add them all together. And that's a lot of numbers to add together. But here's the cool trick about this one. The next two numbers in this sequence are 377 and 610. And the way this works is if I take any, starting at the beginning, if I take any group of numbers and add them together, all I need really is to go 2 more and subtract 1. The sum of these is 609. It's go 2 further, and it's that number minus 1, always. Which is another really cool trick. So if you have a bunch of these that you want to add together, just go 1 more and 1 more after that. That number minus 1 will always be the sum. There's just so many cool things going on here, and they're all kind of interrelated, which is awesome. I want to take a step away real quick from all of that adding. I know it's been a lot of adding, and like I said, it's good practice later if you didn't have a calculator in front of you. But maybe in the comments, that's called Pascal's triangle. And the question is, does anybody know how that's created? It's just a piece of it. This actually goes on forever too. As long as I want to keep adding rows, and you know the rule, you can keep adding rows and it gets really large. But that's just a piece of it. Does anybody know what the rule is, or how do you create Pascal's triangle? And you can type it in the comments. It's actually not so bad and not as complicated as it looks. Each number is the sum of the two above it. So 1 plus 1 is 2. Here's another example. 1 plus 2 is 3. 2 plus 1 is 3. 1 plus 3 is 4, and so on and so on. And that's how you keep adding the rows. You take the two numbers above it, add them together, and that will give you that number that is in between in the next row down. But then you're asking, like, what does this have to do with what we're talking about with the Fibonacci sequence, which is a great question. If I draw diagonals through this triangle and add the numbers together across that line, look what happens. Hopefully these are looking familiar to you. It's our original Fibonacci sequence. 1, 1, 2, 3, 5, 8, 13, 21, 34. So now we've taken this whole other thing, this Pascal's triangle that you've seen before in school, and we've connected it to the Fibonacci numbers, which is really interesting. How all these things are interrelated with one another. Okay. So yeah, it's another thing that you can practice is keep building the triangle and keep adding across those diagonals, and you will get all of the Fibonacci numbers as far as you want to go. So what I'd like to do here, and this is where I mentioned a calculator would be helpful, and I'm going to fill this in slowly as you're working, and some of these are very easy. But those division problems that I set up, where they came from is I'm taking each number in the sequence and I'm dividing it by the one that came before it. So 1 divided by 1, 2 divided by 1, 3 divided by 2, 5 divided by 3, and so on and so on. Okay. And what I would like is for you to, I'm going to put them up here, but if you have, you're writing them down, see what you get. And as you're calculating them, see if you're starting to see there's a number that's starting to form that maybe you'll be able to identify, which is really cool. Okay, so I have some Fibonacci numbers there, and I'm taking each one and dividing it by the one that comes before. Okay. And just like, because the sequence goes on forever, I can keep doing this division over and over and over again. I can keep carrying the sequence out and dividing each one by the term that comes before it. But what you're starting to see is that those numbers are really, really close to one another. And it's not a coincidence. I had mentioned earlier that there's this number called phi. Okay? And we're going to say phi is irrational. Okay. I'll write it that way. So the more division that I do, the closer I would get to that. And you can start to see 1.6, 1.61, 1.5, 1.619, that it keeps getting closer and it actually bounces from below to above and back and forth. It's a little bit less, a little bit more, a little bit less, a little bit more, which is really cool to think about and something you'll learn a lot more about as you get older. But phi is something worth exploring. And I'll mention something that you can use to read more about it. Hundreds of pages of all these really interesting kind of little connections, and it's certainly connected back to the Fibonacci sequence, as you can see. Okay. And it's a couple things for you to try is take this number and divide 1 by it and see what you get. And then I don't have, well, I can make it work. Then if you have a calculator in front of you, take that number and multiply it times itself and see what you get. And something very interesting happens, especially if you have more decimal places. The more decimal places you have, the more accurate it is. But dividing 1 by that number and taking that number and squaring it have 2 very cool properties. And I'll put that in your practice sheet as well, if you want to practice later. One last thing. I promised you that I would show you how to draw this spiral. And what's cool about the spiral is this is called the golden rectangle. The more pieces I have, the closer I get to the golden ratio, which is another interesting thing to think about and to study more. Well, I want to help you draw it. So what you need is grid paper and a ruler and some Fibonacci numbers. So you can see I wrote them at the bottom here, just a few of them, because I only have so much room. But what I'm first going to do is I'm going to draw a 13 by 13 square. And if you have more room, the next Fibonacci number is 21. You can start with a 21 by 21 square. I only have so much room here. Okay. That's 13 by 13. Check. Then I'm going to connect to that an 8 by 8 square. If you have grid paper, it's helpful. You can measure it using inches or things like that too, but the grids are helpful. Check. Then I'm going to draw a 5 by 5. Check. 3 by 3. Check. 2 by 2. And I'm left with 2 1 by 1 squares in the middle. Okay. So that's the first thing. So practice drawing that out. Use a ruler, grid paper if you have it, have some printed out. And like I said, the more room you have, it will always work. You just continue to build out around it. You can put a 21 by 21 square in here too, and it will work if you have the room. Then from here, what I need to do is connect Now, this takes practice, and admittedly, I may not even get this right, even though I've done this a million times because I'm on an iPad and, it's not always the easiest thing to get right the first time. But the more you practice it, you'll start to feel that this is a very natural spiral. It's actually not too bad to draw. It's because the golden ratio is such a naturally occurring thing that even this feels like a natural thing that it almost seems easy to draw. Okay. What I need to do is I need to connect and that wasn't so bad. I probably could have done a little bit better. This here is a little bit crooked, but that's okay. It's something cool to practice, and it connects all this back to Fibonacci and also to the golden ratio. And like I said, the beautiful thing about this is the more Fibonacci numbers you use in this, the closer the relationship between these sides get to this, which is really cool. Okay. So I hope I gave you some fun things to practice. I know that a lot of this was fast. I think this is one where it gives you something to think about, things to create, and take some time with it. And this is a topic that's just just fun with math, and I hope you learned some things that you think were cool and that you'd want to just show other people. And it just really shows you the world around you and the beauty around you can be demonstrated through numbers. So the book that I was referencing is actually called The Golden Ratio, and a lot of what I took was from that book. I mean, I certainly couldn't include all of it. There's so many cool things in that book, but I really hope that you research more about it, if you're a parent or a child, and practice and just explore numbers in a deep way. So with all of that said, I really appreciate you being here with me today. Mathnasium Schoolhouse is every day, Monday through Friday at 11 a.m. Pacific. I will be back next Friday to do some more mental math with you all, so I hope you join me. And with that said, I hope you have a great weekend. Thank you.
It's afternoons that seem to be the most hectic for us, so it was much more convenient when we found Mathnasium at home.
All right, so how do we do half of 5? I think one of the best things about at home is that it really feels like you're almost at home with the student in their house teaching them.
I'm in my comfort zone.
You can just ask for help and the instructor will come right to you.
With Mathnasium at home, I know that they're getting the help that they need.
Awesome, great job.
Mathnasium, changing lives through math.